Okay, empirical formula versus molecular formula. What is the difference? Okay, first of all, what is empirical formula? Empirical formula is the lowest terms you can have a substance in. And molecular formula is the actual representation of a single molecule. And that's a little bit, confusing, but here's a couple examples. I have 4 compounds here: glyceraldehyde, erythrose, arabinose, and glucose. Okay? Now, look at their empirical formula. It's all the same, okay? C3H6O3, that's glyceraldehyde. If we divided everything by 3, we would get CH2O. Okay, it's in the lowest proportions. Let's look at erythrose. Its molecular formula is C4H8O4. If we divided everything by 4 and got it to the simplest ratio, we would get CH2O. The exact same thing as glyceraldehyde. Same with arabinose. Divide everything by 5, we get CH2O again. And glucose, divide everything by 6, we get CH2O. So they all have the same empirical formula because the proportions of the elements with each other are all the same, but they have different molecular formula because they're fundamentally different molecules, okay? Let us look at glyceraldehyde. This is a glyceraldehyde. I'll just initial it, okay? So this is G, E, A, and GL. Okay, so that's a bit confusing. Okay, you can tell by this will be 3, 4, 5, and 6 based on the number of carbons they have. Okay, so glyceraldehyde. This is a glyceraldehyde. It has 3 carbons. It has 1, 2, 3, 4, 5, 6 hydrogens. 6 hydrogens, and 3 oxygens. 3 oxygens. 1, 2, 3. Okay. That's glyceraldehyde. Compare that with erythrose, okay? Erythrose is this molecule right over here. Erythrose is this molecule right over here. It has 1, 2, 3, 4 oxygens, 4 carbons, and 8, 1, 2, 3, 4, 5, 6, 7, 8 hydrogens, okay? So this is erythrose. And when you compare erythrose with glyceraldehyde, okay, they're fundamentally different molecules, right? But the proportions of their elements are the same. Does that sort of make sense? Okay, and same thing with arabinose. This is arabinose. You can see it has 1, 2, 3, 4, 5 carbons. Okay, now glyceraldehyde had 3 carbons, erythrose had 4 carbons, and arabinose now has 5 carbons, but they all have the same empirical formula because the number of oxygens and hydrogens also increased. But they are fundamentally different molecules with different properties. And finally, glucose, probably one of the most well-known organic molecules, ever. Glucose has 6 carbons, 12 hydrogens, and 6 oxygens. So all of these molecules are different. Okay. They each have different chemical properties. They react differently. They, bond to different molecules differently, which is why they have different molecular formulas. But they have the same empirical formula because the elements are in the same proportion. And even if they have the same molecular formula, later on in the course, you'll see that even if they have the same molecular formula, they can have different properties based on the way they're bonded. Okay. But just keep that in mind. Empirical formula deals with proportions, okay? Think of lowest terms. And a molecular formula represents how many elements in each per molecule, per compound, okay? Awesome. Now let's do some questions with empirical formula, and it actually has a lot to do with mass percent, okay? I'll show you the first question. A compound that contains only carbon, hydrogen, and oxygen is 48.64% carbon, 8.16% hydrogen, okay? So imagine you have some amount of, what did I write? Oh, there, this should be a Z, okay? So you have a compound that contains only carbon, hydrogen, and oxygen, and the XYZ represents the subscripts that we don't know. Okay, similar to like a compound like this. Okay, like CHO, we don't know these subscripts yet. Okay. Now what we can do is we can figure out the proportion of each of these elements based off of moles and molar mass. And like, how do you do? And you ask, how do you do that? Well, the first step is you assume the substance weighs 100 grams. Now we don't have to make it as we don't have to assume the compound that we analyzed. If we took a substance of this compound, we don't have to assume it's 100 grams. We could assume it's 80 grams. But notice how when we assume it's 100 grams, it makes these percents really easy to work with, right? Because now suddenly you know that in this 100 grams, 48.64 grams is carbon, right? Because it's 100 grams. The total compound is 100 grams. So if you have 100 grams of a substance and 48.64% of the substance is carbon, then you know 48.64 grams of carbon are in that 100 grams. Same thing with hydrogen. You can just figure out that, okay, there's 8.16 grams of hydrogen in a 100 grams of the substance. And like we talked about with mass percentage, percent composition, these percents must add up to 100. So we can find the percent of oxygen as well, which is just 100% minus 48.64% minus 8.16%, because we know the total percentage of these elements must add up to 100. My bad. So we can figure that out. 64 minus 0.0816, and we get 43.2%. Okay, so let me find my cursor. Okay, 43.2% oxygen. Okay, so let me write that down on my piece of paper I have right beside me so I don't forget. 43.2% oxygen. Okay, so we have all the percentages. Okay, so once we have the percentages, we assume 100 grams, and because we assume 100 grams, we can say that in 100 grams of this mysterious compound that we don't know, 48.64 grams will be carbon, 8.16 grams will be hydrogen, and 43.2 grams will be oxygen. Okay, because we determined that 43.2% of the mass inside that compound is oxygen. And this all comes from assuming 100 grams. We could have assumed 80 grams. We could have assumed 200 grams. If we assume 200 grams, we double all of these values. We double 48.64. We double 8.16. But why do you want to do that? Why do you want to make it, more complicated than it is? So we just assume 100 grams because that's easy to work with. Okay, so once we've done that, next we convert all of these to moles. Okay, in chemistry, a lot of things has to do with converting to moles, and you know how to do that. Moles is equal to mass over molar mass. Okay, the mass we have is 48.6 grams divided by molar mass of carbon, which is 12.01 grams per mole, and we get 48.6 over 12.01. We get 4.046. Okay, so 4.05. Okay, 4.05 moles. Okay, so it's saying this. All this is saying is that if you had 100 grams of a substance, you would produce you would have 4.05 moles of carbon in that compound, in that substance, in 100 grams of that compound. Same thing with hydrogen. You do this and you get a value of, let's see, 8.16 grams divided by 1.01, which is the molar mass of hydrogen, and you get 8.08. Okay, so we get 8.08 moles. And you do, same with oxygen, you do 43.2. So how much mass of oxygen in 100 grams of this mysterious compound divided by the molar mass of oxygen, which is 16, you get 2.7. 2.7. Okay, awesome. And then what you do is, let me write these numbers down. You get 4.05 carbon, 8.08 hydrogen, and 2.7 oxygen. Okay. Now, you take these numbers, take 4.05 mole of carbon, take 8.08 moles of hydrogen, and finally 2.7 moles of oxygen, and you divide by the lowest number of each of these. So in this case, it would be 2.7. 2.7 is the lowest number, so we divide by that. We divide all the numbers by 2.7. So 4.05 divided by 2.7, you get 1.5. 8.08 divided by 2.7. 8.08. Let me type that into my calculator. You get 3. You get 3. Okay. And let me write that 2.7. And obviously 2.7 divided by 2.7, that's just 1. Okay. So now we have 1.5, 3, and 1. This is the ratio of carbon to hydrogen to oxygen. Okay. So we were almost there in finding the empirical formula. Because remember, empirical formula is just talking about the ratio of the elements. But here's the problem. We have this 1.5 here. You know, an empirical formula, you never see C1.5 H3O, right? What you do see is C3H6O2. So you multiply everything by 2, and you get a nice ratio of 3 to 6 to 2. And this is the carbon in moles compared to the moles of hydrogen compared to the moles of oxygen. So that's the compound. You get C3H6O2. This is the mystery compound that we were looking for. Okay? That's how you deal with empirical formula. Now keep in mind, this is not the molecular formula, okay? The actual compound we had might have been C6H12O4. Okay, it might have been this. We can't tell. We don't know for sure yet. All we know is the empirical formula, the lowest common ratios we have is 3 to 6 to 2. And from that, we can figure, we have the empirical formula. We know nothing about the molecular formula. All we know is about the empirical formula, because empirical formula deals directly with the proportion of elements you have compared with each other. Okay? And, you know, once again, the reason we can do this is because we converted everything into moles. Okay, moles are really important because moles is, you can sort of think of it as a proportion of elements with each other, right? If you had if you had 3 moles of carbon, you had 6 moles of hydrogen and 2 moles of oxygen, they would make 1 mole of C3H6O2, right? In this case, or it would make half a mole of C6H12O4, okay? You don't know which one. All you know is the empirical formula, you can make this much. And that's why by converting to moles, you can figure out the empirical formula.